Hi, I'm Professor Goins. In this video, I'm going to look at geometric series. In particular, I'm going to introduce what a geometric series is, look at a formula for how to evaluate them. First thing I'm going to do is I'm going to take this polynomial term r to the fourth minus 1, and I'm going to divide that by r minus 1. Now, traditionally, we use x for my polynomial variable. In this case, I'm going to use r, as is traditional with geometric series. All right, set this up with synthetic division. So I've got the 0 of the divisor goes in my half box, and then I list the coefficients of my dividend, and then I run through the synthetic division. Remember, the leading coefficient drops down. We multiply these two values, the number in the box, the number down here, which is 1, that goes to the next column. You add vertically, and then 1 times 1 is 1, that goes to the next column. You add vertically all the way down to the end. And then the conclusion is that these values right here are the coefficients of your quotient with a remainder of 0. So if I take r to the fourth minus 1, I divide that by r minus 1, I get this cubic polynomial here. So coefficients of 1, 1, 1, 1, which is 1, 1, 1, 1. This is the coefficient of r to the third, for example. Okay, you could imagine that if I was to make this a 5, for example, then if I take r to the fifth minus 1 divided by r minus 1, I'm still going to have all these 1's here, and that would give me an r to the fourth plus r to the third, etc. Generalizing that, if k is any positive integer, and I take this polynomial term of degree k, so it's r to the k minus 1 over r minus 1, what's going to happen is I'm going to generate 1 plus r squared all the way up to r to the 1 power of 1 less than this one. So in this case, this was r to the third. I took that up to this was r to the fourth, and I was able to go up to r to the third. The series, however, does go, let's see, no, it goes in the right. It goes in the opposite direction of this. So the first term would be r to the 0, which is 1, and then plus r squared, which addition is commutative, but it represents the same sum. What I then want to do, I'm going to assume that the value of r has an absolute value less than 1. So it could be a half, it could be negative 2/3, but it can't be 2, 4, 5, or even 1.1. It has to have an absolute value less than 1. Then what I'm going to do is I'm going to take the limit of both sides as k goes to infinity. If I take the limit on the left-hand side, what happens is r to the k is going to go to 0 because the absolute value of r is less than 1. Okay, so this is going to give me negative 1 over r minus 1. And then if I take the limit on the right-hand side, nope, that should be r to the n. The index variable here should match this, so this should be r to the n. Sorry about that. Okay, take the limit as k goes to infinity of this finite series. It turns into an infinite series. If k goes to infinity, then k minus 1 goes to infinity. This would give me the sum n equals 0 to infinity of r to the n. Therefore, this infinite series is equal to this value. And notice what I have here. I've got a negative 1 on top and then r minus 1 on the bottom. Well, I could multiply top and bottom by minus 1 and rewrite this as 1 over 1 minus r. Therefore, this infinite series is equal to 1 over 1 minus r, again, when the magnitude of r is less than 1, when the absolute value of r is less than 1. All right, let's summarize that on the bottom here. This gives me the infinite series of powers of r, so 1 plus r squared plus r cubed, etc., is equal to 1 over 1 minus r. And this is the formula that we will use. Let's find the exact values of some of these series here. And again, these are called geometric series. All right, start over here, solution. part A. What I have to do is I have to manipulate the expression inside the series so that it has this form here, r to the n. What I'll do with 1 over 2 to the n is the following. I'll write this as the sum, n is equal to 0 to infinity. 1 is the same thing as 1 to the n, which means I can write this as 1 over 2 to the n. And now I notice that this is my r value. Okay, so this would be the value that I plug into this formula, giving me 1 over 1 minus a half, which is 1 over a half, and 1 divided by a half would be 2. This infinite series then converges, because it has a finite value, and it converges to the value 2. Let's clean up the other side of the board, and let's work through the rest of those. Part B. I've got a 2 to the n on top, and then on the bottom I've got 3 to the n plus 3. What I'll do is I'll write 3 to the n, or 3 to the n plus 1 as 3 to the n multiplied by 3. This would give me 2 to the n over 3 to the n times 3. 2 and 3 here both have that common exponent, which means I can write this as, well, you pull this 1/3 out front here, and then I would have 2/3 to the n. Constant factor inside of a summation can be pulled out front. This now has the form of a geometric series, where r, in this case, is 2/3. Plugging that into the formula, I get 1/3 and then 1 over 1 minus r, therefore 1 over 1 minus 2/3. This gives me 1/3 multiplied by 1 over, well, 1 minus 2/3, this would be 3/3, that would give me a 1/3. Multiply those fractions together, I get 1 times 1, which is 1, then 3 times 1/3, which is 1, 1 over 1 is 1. The value of this infinite series then is 1. Part C. What are we going to do here? Well, in this case, I've got 3 different locations where I have a power of n. Let's rewrite that as follows. Sum n equals 0 to infinity. I would have minus 3 to the n, so I'll leave that alone for the moment. And then 2 to the n plus 1, I can write that as 2 to the n multiplied by 2, and then times 5 to the n. Let's group together the terms there that have a power of n, giving me this 2 in the denominator, that 1/2, I could actually bring that out front. And then everything that's inside, minus 3 over 2 times 5, all of those had a power of n. All right, and now I can use my formula. I would get 1/2 multiplied by 1 over 1 minus, and then it's right as 1 minus r. In this case, r would be negative 3 divided by 10. Which would give me 1/2 multiplied by 1 over. Minus minus, of course, would be a plus. 1 plus 3 over 10 would be 13 over 10. Multiply those fractions straight across. Let me clean up the middle here so I have make sure I keep that on screen. multiply straight across, 1 times 1 on top. And then I'm going to have 2 times 13 over 10, which would give me 13 over 5. Which is 5/13. Okay? That was part C. This infinite series here, C, then reduces to, or it has the value of 5/13. Part D. Notice what's different with part D. My infinite series starts at 1, not 0, which is what I just erased. All the other series for my formula for the geometric series has a starting value of 0. Therefore, what I have to do is I have to start by manipulating this index here so that it starts at 0. All right, n equals 0 to infinity. If you're not sure, if you haven't seen how to shift an index, watch the video that I posted on shifting the index of a series. Really quickly here, if I take the initial index value and it goes down, then that means that the index variable in the expression goes in the opposite direction. If I shift this down, this goes up. If I shift this up, this goes down. So they go in opposite direction. But feel free to watch that other video if you need some more explanation there. All right, if this goes down to 0, that goes down, this goes up. Therefore, I would have 5 times 3/4 to the n plus 1. Quickly check, if I plug 0 into this for my very first term, I would have 3/4 to the 0 plus 1, so 3/4 to the first. Over here, if I plug 1 in, my first term, I'd have 3/4 to the first, so that matches. All right, now what I need to do is I need to make this to the nth power. That means I can pull off a factor of 3/4. And then 5 times 3/4, which would be 15/4, is a constant factor, and constant factors can be brought outside of the summation. And then I would have my infinite series in the same form that we had in the formula that we came up with. Okay. R in this case is 3/4, and therefore this gives me 15/4 multiplied by 1 over 1 minus 3/4. 1 minus 3/4 would be 1/4. Therefore, when I multiply these fractions together, notice when I multiply 4 and 1/4, I get 1. On top, I get 15 times 1, which gives me a value of 15. And then finally, let's work through part E. Clean up over here. Okay, so part E, find the screen here, about right there will work. Well, what do I have to do in this case? Once again, I'm going to have to shift the index here. I have to bring this down to 0, so from 3 down to 0, that means that index variable is going to have to go up by 3. All right, this gives me the following. The sum n is equal to 0 to infinity of 5 over 2. Now, if this index, the initial index drops by 3, what I do is I replace n with n plus 3. And then I already had a plus 1 there. Okay? And then what I'll do is I'll rewrite this as the sum n equals 0 to infinity of 5 over 2 to the n plus 4. And then I can pull off a factor of 2 to the 4th. In the denominator, so 1 over 2 to the 4th. We could also bring that 5 out as well. and then that would be 1 over 2 to the n. 2 to the 4th would be 16, so I can bring out 5 over 16 in front of the summation. And then I'll rewrite 1 over 2 to the n as 1 over 2 to the n. Now we can wrap it up and use my formula. 5 over 16 multiplied by 1 over 1 minus r, which is 5 over 16 times 1 over a half. Multiply straight across. This would give you 5 over 8. 16 and a half would be 8, 5 and 1 would be 5, and therefore 5/8 is the value of